because we're such a multidisciplinary program, we also have the opportunity for both our MA and our PhD students to do interdisciplinary work.
A lot of our greatest ideas have risen out of friendly conversations in cafes with our professors, and this nature of interaction is what makes the department bigger.
The basic objective of the department is to impart knowledge to enable the students to face the real world.
Hello and good day to everyone. Thank you for joining us today. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutes and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the Institute of Eminence. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. As a part of these initiatives, the IRS webinar series aims to showcase the innovative research being generated to various stakeholders like the students, researchers, industrialists, and policymakers. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 39th webinar from the IRS webinar series. My name is Richu George Philip, and I'm a part of the Office of Global Engagement. From the Microelectronics and Integrated Circuits Technology Cluster, the research initiative presenting today is OLED display technology led by Professor Devdatta Ray. OLED-based displays offer improved image quality, faster refresh rates, superior contrast, wide color gamut, lower power consumption, and full viewing angles compared to LCD-based displays. With this project, the aim is to create technology differentiation by using their proprietary proximity deposition process to develop next-generation AMOLED displays. Professor Devdatta Ray is an associate professor at IIT Madras. His research is on organic optoelectronic devices. His group in IIT Madras studies organic semiconductor-based transistors, light-emitting diodes, detectors, and solar cells. They work on growth, design, and the understanding of fundamental and technical aspects of these devices. Professor Devdatta and team have recently set up India's first AMOLED laboratory in IIT Madras. In this facility, which is co-funded by public and private organizations, they aim to find technical solutions to enable the manufacture of AMOLED displays in India. And as the moderator for the event, we have Dr. G. Rajeshwaran with us today. Dr. Rajeshwaran is a professor of practice at the Department of Electrical Engineering, IIT Madras. He is also the founder, director, and CEO of Grantwood Technologies Incorporated USA and Grantwood Limited Hong Kong, and director of Grantwood Technologies Private Limited India. His field of interests are displays, solid-state lighting, photovoltaics, corporate strategy, global alliance, manufacturing, product commercialization, and industry creation. Dr. Rajeshwaran is an elected fellow of the Society of Information Display for pioneering contributions to the development, commercialization, and manufacture of AMOLED displays, and credited with the funding of more than 30 billion AMOLED display industry. He has over 100 plus publications, presentations, invited talks, plenary lectures, and short courses in the fields of OLED-based flat panel displays, LEDs, and solar cells, and also have 16 granted US patents. Thank you for being with us today, Professor Rajeshwaran. We're very excited that you could be a part of this session. We also have Professor Soumya Datta, G. Venkatesh, Khadir Khan, Inakshi Bhattacharya, Amitava Das Gupta, Dilip Nair, Anjan Chakravarti, and Nandita Das Gupta on the panel with us today. A warm welcome to all of you. So before we start, a note to the participants, please use the Q&A to enter your questions and upvote questions that interest you so that the moderator can prioritize them later. Over to you, Professor Devdatta.
Yeah, thank you, Richu, for the introduction, and I hope I'm audible. My voice is clear, I'm guessing. Yeah. So what I'll do is that I'll start my presentation. I'll let me share my screen first. This will enable me to discuss with you about today's topic, which is OLED display technology. Is my screen visible?
Yes, it is. Yeah, it is.
Yeah, let me make it full screen and let me use a pointer. Yeah. Okay. So thanks again. And what I have planned for today's talk, which is for 15 minutes, and then we can have we can have some Q&A after that too. Is to give you a little bit of a background on OLED displays and a little depth in the technology front, right? So, of course, you are looking at it from the AMOLED display point of view, which has both a scientific or technological side as well as a business side, given the fact that it's one of the hottest uh, technology right now, where you are actually which is information transferred to you from a source, right? And this source could be of any size, shapes, as well as either mobile or static. So I'm going to give you a bit of the technological end, and I'm not going to talk anything about the business end, at least in this seminar. This is my contacts, and this is my email also here. So if there are any questions afterwards, you can always address it to me. I'm Devdattare. I'm from the Department of Electrical Engineering, and I am also part of two Center of Excellences. One is the AMOLED Laboratory in IIT Madras and the Center for MEMS and Nanophotonics in IIT Madras. And what I'm going to talk about today is next generation AMOLED displays, while I'll be focusing more on the OLED part of it and the kind of research which is going on currently in both OLED and a little bit on what we plan to do for the AMOLED displays. So that's our agenda for today. This is the aim of the center, right? So the center, which is the AMOLED Laboratories Center for Excellence. And what we plan to do is to develop AMOLED display manufacture in India, right? Just to give you a bit of a background, the way AMOLED, the technological bit I'll come to at the end, but typically this technology requires something which I call mega factories, right? So when you are, let's say, looking at your AMOLED display on your phone, for example, your smartphones, a lot of you have AMOLED displays on your smartphones. And these may be small in size, which means that it may be 5.5 inch, or maybe it's a watch, for example, which may be, let's say, an inch, a little bit more than that. And these are not made individually, right? So typically, what this company does, for example, let's say you are buying let's say one of these devices, let's say from Samsung, let's say, or maybe LG or someone else, or an Apple display, sorry, a phone. What happens here is that, so to make this phone displays, what's done is that you actually start off with a much bigger substrate, which could be of a dimension of 2 meters by 1 meter, and you grow many, and I'll show you how to grow, or how does one grow devices on top of it, and then you cut it, and you then use one for each whatever device it goes into, right? Maybe a watch or maybe a phone, right? This means that you have to have a lot of capex if you want to enter this business, and this is a business which is quite mature, and in order to if you want to have people interested and to diversify this business, let's say, over multiple manufacturers, you need to come up with some new technology, and that's why I call it disruptive, and we hope it's going to be disruptive technology in order to reduce the capex, right, the capital expenses, so that people can actually get into this business. You can motivate and encourage and have some enthusiasm into new industrialists who would like to get into this business. So this is what we plan to do. We plan to come up with a new technology which will change the way these devices are made from what is done in the state of the art, right? So I'll give you a little bit of that near the end of my lecture. And of course, enable R&D for the next generation AMOLED displays. So what is next generation? I'll also talk a bit again while during the talk. Okay. So there are a couple of AMOLED is if you open up this one, it's called active matrix organic light emitting diode, right? So basically, if I cut this word into two, you have this OLED, which is organic light emitting diodes. I guess most of you have already heard of it. And this AM is something which is called active matrix. It defines how these OLEDs are being turned on and off, which is defined by what goes below the OLED. All right, so I'll also come a little bit into this in the lecture. Okay, so a bit of a background as to what organic semiconductors are. So organic light emitting diodes are made up of something which is called organic semiconductors. Okay, so these are not, we are not talking biology here. Organic is, you know, if you remember your school chemistry, this is basically organic carbon-based molecules, right? So on the right-hand side, I have a molecule. Is just an example which I took. It's one of the earliest molecule which was used in an OLED. It's called ALQ3. So this is a molecule. It's a stable molecule, right? So this is an organic molecule, right? It's still not a semiconductor yet. It's just a molecule hanging in there. And on the left-hand side, just for comparison, I'm showing you a silicon, lattice, which is, of course, the silicon is a semiconductor. It's a doped silicon. And, as you can see in here on the left-hand side, that the silicon atoms are bound together by very strong covalent bonds, right? So you have this nice crystalline crystals which can be formed. While if you look on the right, if you can think of one of these organic molecules as, let's say this ball in here, right? So they are just put next to each other when you're making a film, right? So we need to make a film, right? It's solid state, right? So solid state devices. So these organic molecules are stacked next to each other. And since they are stable molecules by themselves, they are held together by something which is called, van der Waals forces, and these van der Waals forces are weak forces. Okay, so while this silicon and this silicon has a very large, overlap of wave function, these do not, right? I'm going to talk a bit on physics, a bit of engineering in this seminar, and hence, there's a very little overlap of wave function between each of them. And hence, if you want to go a little bit more deep into the physics of what's happening, on the left-hand side, for an inorganic semiconductor, you end up with, conduction bands, valence bands. These are bands, right? So this is the band edge, and then you have the band. So you have a lot of delocalization because of this overlap of wave function, and hence, these carriers, if you can put an electron disk in the conduction band, you can move very nicely with large enough mobilities. While here on the right-hand side, if you're looking at this organic I would say organic molecules to begin with, and then let's say you made a semiconductor out of it by stacking all these molecules together, you end up with something, even in the molecular sense, because they retain a lot of their molecular properties, something which is called, in place of a conduction band, lowest unoccupied molecular orbital, where it's like a conduction band, although it's not band-like, it's the molecular level, and highest occupied molecular orbital. So basically, this is like a valence band where you are filled up with electrons, and there are, of course, no carriers in here at t is equal to 0. And hence, they retain a lot of molecular properties, right? So on one hand, on the left-hand side, you have something which is a highly localized semiconductor. On the right-hand side, you have something, which, there is a lot of localization because a lot of molecular properties are retained, right? So what happens is that, if you want to now put it in more of a physics perspective, what you're doing is that, if I'm plotting space on the x-axis and energy on the y-axis, you have all these energetic states, the electronic states, which are distributed in energy, and you can have some kind of a dispersion because of certain, let's say some electrostatic properties coming in, and hence what happens is that you don't get one single energy, you get a dispersion. So something like this, which may be, let's say, a Gaussian or something like that. So this is your density of state, right? So these are your states. So this is like, let's say, something like a valence band, and this is like a conduction band. Okay. So what this does is that for an organic semiconductor, since these semiconductors retain a lot of their molecular properties, once you have you excite this semiconductor, right? So let's say somehow you excite it so that you have an electron in the in the upper, let's say in the LUMO, and the hole in the HOMO. They are actually bound very strongly, right? Because they retain a lot of their molecular properties, and hence they form something which is called a very stable exciton. An exciton is nothing but an electron and hole. It's like a dipole, right? So this is a dipole which is bound together. In an inorganic semiconductors, these excitons have very low binding energies, which means that at room temperature they will break, which means that it's very difficult to get light out from let's say something which is band like this, right? Because you have an electron in here and hole in here, they'll be free, they'll move, they won't recombine to give you light. While on an organic semiconductor, these are bound very well, so they will recombine and give you light, right? So these are, if you can think of it, something like little quantum dots. And in an inorganic semiconductor, let's say let's say the displays which has a white backlight and let's say LCD on top of it, color filters in order to make a display, they typically are made of quantum wells, or if you can also use quantum dots. So what you do is that somehow you have to have these electrons and holes see each other for long enough in some bound state, and then this gives out light, right? So this means that you are making some kind of a quantum well kind of a structure. And then of course, once you start making quantum well, your cost goes up, right? Because you need to have, I'm not going too much into detail. If there are questions, we can take it afterwards. But basically, the growth process becomes very, very expensive. And hence it becomes quite expensive as well as difficult in order to realize, an emissive device. While it's quite easy in here because, you have excitons to begin, okay? So what this does is that organic semiconductors, since they are so much excitonic, materials, it makes it very easy to make light emitting diodes. Okay, I'll show you the structure afterwards. So on the left-hand side, which is an inorganic, what you're doing is that in order to make a light emitting diode, you have to have, this nice quantum wells, which means that you have to be careful about crystalline quality. Otherwise, if you have states, it may lead to quenching of, it may lead to, non-radiative recombination, which means that you will not get any light output. So this means that you have to have nice lattice match structures, could be pretty expensive, and you cannot have pixel definition, which means that, in a LCDs where you do have a white light backlight, the LCD is made up of, it's on top, these are color filters that you have to turn on and off, right? So basically the white light is always on, and then you're turning on and off a pixel with color filters with the red, blue, and green in order to get some color out, right? So on the right hand side, what I'm showing you is a pixel definition. Is one of the pixel definition. You can have many types of pixel definition. It's just an example which I have picked up. So this shows you a pixel definition of an AMOLED display. So you have red, blues, and greens, and you can turn them on and off or in different intensities to get what kind of color you want from a pixel, right? And just to give you some perspective, this dimensions in here, let's say the blue, for example, that width is something like of the order of, let's say, 20 to 30 microns, right? So that's like 20 to 30 microns. And this means that, you are you're really cramming in a lot of pixels in your phone. A pixel number of pixels goes into millions, a couple of millions, for example. And hence, what you can do is that you can have many advantages. One is you have a perfect black, because if you want to have a dark spot, what you do is that you turn off that pixel, and you can, of course, since you have all these different color material to choose from, you can have very beautiful colors, which means that you can reproduce whatever image you want to do very well in an AMOLED display. Plus, it's quite much more cheaper to make, because you don't have to make any quantum well or quantum dots, because by itself the organic semiconductors behave like quantum dots, right? And you can actually engineer the material, which by chemistry, and then you can define whatever red, blue, or green pixel which you want. Okay, so there are all these different advantages. So these are some which I talked about. So basically, our aim is to make pixels like this, right? And somehow pattern them. Okay, so I'll come to this patterning afterwards, how to pattern this red, blue, and green near the end of the talk. But there are two things now which one needs to do. Skip this. Is that hello?
Oh, really?
There are two things which one needs to do, which is make these OLEDs, right? So each of this red, blue, and green are actually light emitting diodes. So we need to make nice, efficient, high brightness OLEDs, as well as OLEDs which has the color which you want, which means that a pure red or a pure green or a pure blue. Okay, so this is our aim. Typically, this is how an OLED look like. So, okay, this is the simplest OLED. This is the first OLED which was made in the 80s, right? So what you have, this is like a sandwich. It's like a burger in some sense. Okay, so it's just like a sandwich. So what you have is a contact. So this can be a substrate, right? So let's look at it. So basically, what happens is that the light will come out, let's say, either that way or that way. So this whole thickness, right? This whole thickness, which I'm showing in here, This could be of the order of, let's say, 100 nanometers, right? So we're talking about 0.1 microns. Okay, it's very, very thin. So you'll have a contact, right? A contact by which you can inject your, let's say, holes, for example. Then you have layers in here, some layers which will have these holes or these electrons move freely. And then they will go to a layer which is called a emissive layer. Okay, it's called EML, emissive layer. So this is where the magic happens. This is where the color is defined and the light comes out. Although the arrows are shown in here, that you would like to have the light come out either this way or that way, depending on what kind of OLED which you are designing. So what you need to do is that you need to have these holes and electrons flow smoothly and balanced in this interface. Let's say the electron goes in here and then meets the hole. It forms this, so something which is called an exciton, right? Basically this dipole, and then they recombine radiatively and gives out light. Okay, so and these electrons and holes in the semiconductors are called polarons because they are not truly free, right? Because they are not really moving in a extremely free delocalized semiconductor. They are in some sense bound in a polaronic state, which means that they are polarizing their surroundings and falling into a well, and hence they're moving with low mobilities, but they are moving and forming this exciton, right? So basically what you're trying to do in an OLED, and this is what we study, right? So this is what our group studies, and this is what we try to make better, is that we need to make nice transparent conducting contacts, right, in order to have the injection. Then we need to understand how does charge carriers flow, right? So that we need to have absolutely nice electron and hole balance, so that you have a very good efficiency of the device. Then you need to enhance this exciton efficiency, right? So this is the number of excitons which you make and the way these excitons give out light. And then you also need to look at new methods for device application, right? So at the end of the day, what we need to do is make high efficiency, high intensity, cheap next-gen devices. Okay. So so for example, I've given you this example. I won't go too much into detail at this point in time. So let's say this is one of the, let's say, a red OLED device, device which is made by us. So you can see in here that on one side you have a contact, on another side you have a contact. Then you have this many different layers. Okay. And all these layers put together will make your light emitting diode. Okay, and so for example, this is a red light emitting diode. It's got very high efficiencies. This is, for example, a blue light emitting diode, right? So this is pure blue. In fact, this is the exact blue which you want. And if you want to see it from a color scheme, which I'm showing in here, so in the color gamut, what you want to have is that you want to have a pure blue, a pure green, and a pure red. So that you want to have a large area in between, so that if you want to have a, let's say, a color which is here, or a color which is there, or a color which is there, you turn on your red, blue, and green pixels in such an intensity, so that you reproduce the exact color which you want to do, right? However, these OLEDs sometimes lose their efficiency, right? So this is efficiency as a function of intensity. So this is called intensity. Typically, your AMOLED screen will have a max intensity which is in here, 1000 candelas per meter square. Sometimes this is also called nits. Okay, 1000 nits. You may be operating it in here, like 200 maybe. You're not operating at the full intensity, but this is the max intensity. You can see that EQV goes down from the max as you go higher and higher. So what we also need to do is that we study, okay, again, won't go too much into detail, how do these excitons actually quench? Okay, so for example, we study how do these exciton interact with carriers, which leads to quenching processes. Okay, so if you have any questions on this, you can of course read our papers, and we can and of course ask me later too. So basically what we try to do is that we need to decrease this quenching process between excitons and polarons, and so that what happens is that we would like at the end of the day to have an EQV which looks like this, okay, flat, so that at whatever intensity you drive your OLED, the efficiency should be the same. All right. Then we also try to look at transport, right, carrier transport. So for example, you can engineer carrier transport in this materials. Transport is a big issue because if I go back to the screen, you need to have this holes move nicely. You need to have these electrons move nicely, right? So what we need to do is that we need to engineer transport, and this you can do by changing, for example, the morphology, right? So here I'm showing you different morphologies grown into. So the way you grow change, defines what kind of morphology you end up with. And then we try to study how do this morphology, the crystallinity affects your mobility, right? So for example, this is for a material which has one of the highest mobilities, not the highest, but nearly the highest mobilities. As you can see, the mobilities are not very high, right? So this is 1 centimeter square per volt second. So you can see that the mobilities are much smaller than what you see, let's say, in silicon. However, it works because we are working with very thin samples, 30 nanometers, 20 nanometers, something like that. And hence, then what we do is that once you engineer the carrier transport, then what you can do is that you can design your OLED, right? So we also work. I just wanted to give you a flavor of what we are doing, working on, and which is leading together in this full system, which is an OLED, is to find out new transparent conducting contacts, right? Because you need to have light coming out of your OLED, right? So a solar cell, for example, will have light going in, while an OLED will have light coming out. So you need to find out cheaper ways. For example, graphene, there could be a cheaper way of making transparent contacts instead of what is used right now. And what we do is that we try to use graphene as transparent conducting of oxide. And yeah, so and this will help us to go forward towards the next generation of displays, right? So you need to dope graphene, of course. You need to enhance the conductivity, and these are some things which we are working on. And we also try to make new ways by making large area devices. Okay, so CVD may be a new way. Okay, so chemical vapor deposition. So this is a very a topic which there's a lot of open space because it is not being studied much. But we do have seen a lot of very interesting results. So maybe CVD can help us make certain layers over a large area very efficiently. Okay. So that's the little background. I won't dwell too much on the background of the OLED, but basically these are the different layers of where you study on the light emitting diodes. And what this project does is that we want to make AMOLED displays. We want to give turnkey solutions, right? It's not just coming up with an R&D, but really turnkey solutions where we would like to go away from the state of the art, which is the state of the art, which is the mega factories, which you see, let's say in Korea, right? Samsungs and LGs, right? Where what you do is that you start from a very large mother glass, which may be 2 meters by a meter of that size. You grow multiple devices and then cut it, right? So you end up, investing a lot of money. And what we are looking for, and what we're doing in this project, is to create modular factories, right? So this is what we want to do. We want to create modular factories where if you have you don't have to put that kind of an capex. You can work with a capex which could be a 100 times that. You may be producing less, but you are going to make the same profit or maybe a better profit margins, because we think that our new deposition technique, which is a maskless deposition technique. So what this does in this first scenario is that you put a mask, right? So mask basically is just like a mask. It's like putting a mask. You basically put a mask and then you grow your red, blue, and green through the mask. It's a process which takes a lot of time. It's a very difficult process to master, and of course it makes that's the reason you start with a very large mother glass, right? Because you need to produce a lot of displays within a certain amount of time to actually profit. So what we are proposing is a maskless. It's a new technique. We call it proximity transfer, where we are transferring the material in close proximity, and it's maskless too, which means that you don't waste your time putting in a mask, and you can make things very fast. Okay, so we are working with our joint JDP Ground Food Technologies, and already we have achieved some bits. So for example, what I'm showing you here is our new laboratory. So this is the new laboratory, and this is one in the world. This is what I can say, because in our laboratory, there is no. I mean, this is the only laboratory in an university setting, right? I mean, of course, companies like Samsung and LG work on these displays. Universities do not really work on displays. So this is perhaps the only laboratory in the world where we have designed our display machine. So these are basically in here where we'll be able to make displays by the state-of-the-art method, which is with a mask, right? So you need to have a benchmarking, right? So basically we will be able to do it with the state-of-the-art mask process, and the new proximity material transfer process, where it's a maskless process. It's a very fast process, and what we should be able to do is that we should be able to meet the same specifications which one gets from the state-of-the-art process, which is using a shadow mask technique. Okay, so this is ready, and this is where we are going towards. We are going towards displays which will be more efficient by either by new molecules or cheaper, because we'll be wasting less material. So we believe that our proximity material transfer process will lead to just 15% loss of materials, while the current generation has a 85% loss of materials, only 15% utilization rates. Okay, so we believe that that's going to reduce a lot of cost, given the fact that some of these materials are pretty expensive. This is one of our OLEDs, for example, grown in our system. Is very bright green OLED. This one, in fact, is glowing at roughly 6 or 7 times the max intensity which you see in your smartphones. Okay, so basically we'll be transferring all of this technology towards the device. So that's what we are going towards, right? So we are ready, and then our next step will be to just like I showed you, get all this, refine all the technologies which we have, which I showed you all the science, and then put together to make these displays with the state of the art as well as new technology. So I'm going to stop in here, and then we can have this Q&A. But I would like to thank our funding agency. So we are funded both by public as well as private entities. And I'll stop in here. And if there are any questions, I'll be happy to answer them. And there are certain questions in here. So Rishi, shall I take these questions one after the other, or?
Yes, Professor Deepta, sounds good. We can do that.
Okay. All right. So let's see. Okay, so I'll go one after the other. So Dhruv asks what technology is used by Samsung in their folded phones. So actually, this is the same technology which is used even in their normal phones. Okay, so I mean, of course, a lot of their technology is protected. It's not that you can walk into Samsung and exactly find out what the technology is. But at the end of the day, what you have is that even your it's the same technology which goes into your curved the smartphones, where you have the curved sides, right? And if this smartphones where it's not a flat, exactly flat display, right? It's flat, but on the edge you have this curved edges. So basically what you do is that you have a polymer, and then you grow the display on the polymer, and this polymer is now basically stuck on top of a certain substrate. So this polymer can of course now be folded, right? Because it's a polymer substrate, so it's an flexible substrate. However, once you start flexing, after flexing it a certain number of times, your efficiency starts to go down. And hence, when they first came up with this phones where you have this bent, this curved edge, that's more of a conformable display, right? So your display is conforming to your substrate, and then there's of course no bending, so it lasts for a much longer time. Once you go to a folded thing, of course, that thing is it becomes much more difficult because of this the degradation which can happen because of this folding. I guess that answers. How do I make these questions go to answered or something like that?
At the Q&A box.
Yeah, I'm at the Q&A box, but how do I?
You can see the questions in the open.
Yeah, I can see that. So can I make it go towards answered by some way?
Yeah, if you click on it, you have an option to dismiss or delete. So you can dismiss the question perhaps after answering it.
Okay, all right. Yeah. I see. I can do it now. Yeah. Okay. So that's done. Okay. Let's see. I think Raj also typed. Samsung uses AMOLED displays in most of the smartphones, including. Yeah. I guess that's right. Yeah, that is right. So this technology is used for marine. I don't know what is marine is. I don't know what is meant by marine applications. I mean, we're talking about displays in here, so I don't really understand that question per se. What are the criteria parameters we should work on to improve refresh rates in the screen? So there are a number of, so you can go towards higher refresh rates, so that a number of things. Of course, I'm looking at only from the hardware point of view at this point in time. So this displays, I mean, the OLEDs are grown on a substrate. So basically, there's this active matrix, right, which I did not talk about, which is basically the substrate, and which has switches, which is basically turning on and off your OLED at a certain level of intensity in order to reproduce whatever is the color which you want. And depending on what material which you use in that, that changes the refresh rates, plus the number of pixels which you have crammed in will also be will change the refresh rates, and any kind of RC which arises could affect your these frequencies. So while the refresh rates are quite good for these smartphone kind of pixel densities, if you go to certain displays where the pixel densities are much higher, then of course this has to be looked into, and then one may have to go away from the technology which is right now, which is low temperature polysilicon, to something maybe different, which with higher mobilities in order to uh, you know answer that problem. How can we engineer such materials? So that's up to the chemical engineers. So many chemical engineers, chemists, synthetic chemists work on it, and there are thousands and thousands of materials. But of course, sometimes it's good because you have different materials, huge library from where you can choose materials. Sometimes it's bad because there's too many materials, right? And then it becomes difficult as to find out exactly what is good or what is bad. So there are lots of materials. There are next generation of materials where you can go over the limits of efficiencies which you see. For example, the blue typically uses something which is called a fluorescent OLED, while the red and the green uses something which is called a phosphorescent OLEDs, where the phosphorescent has much higher efficiencies because of certain things, which I'm not going through too much in detail today. It's called singlets and triplets. So the triplets are also harnessed, the kind of excitons. And then there are this next generation of materials, but of course phosphorescent OLEDs have their own problems about how good a color quality is. The color quality is not as good. Blue is very much it's much better because it's a fluorescent OLED. So then there are this next generation of materials called TADF, thermally activated delayed fluorescent materials, and hyper fluorescent materials. So these are some things which are not used in the current state-of-the-art mobile phones, or sorry, on the AMOLED displays. But we believe that we are also working on them. In fact, the red OLED which I showed you in my talk is a TADF material. It attains 13%. That's like 65% internal quantum efficiency. You're limited to only 25% in fluorescent. Okay, so those we believe are the next generation of materials. But then again, some of them do have issues about how good a color quality is. So that's something which everyone's working on. Shared screens not visible. I think it was visible, I think, right? Otherwise, someone would have stopped me. How AMOLED and OLED are different? They're the same. Basically, OLED is just organic light emitting diode, while OLED, which is lying on top of an active matrix substrate where you're driving the OLED or the pixels, that's called an AMOLED. Okay, so at the end of the day, these are, I mean, there's OLED in there, right? Both of them has OLEDs. Okay, which technology used in electric vehicles? This is again, I think you're in the wrong seminar. So I guess there may be a seminar on electric vehicles, and I think you should sit in there. Why some AMOLED displays have low response time, and why most of the AMOLED used in cheap phone hands? I don't think there is any AMOLED displays in cheap phones. Because AMOLED displays are more expensive than your LCD displays. But having said that, they are not very expensive. Okay, so they have their cost has come down quite a bit. So you can still find good AMOLED phones with AMOLED displays in the range, even in that 12,000-15,000 rupees range too. Okay, earlier it used to be only in the 40,000 rupees range and higher. So, but generally the hanging is not because of the display. It has got to do with the drivers or maybe the whatever is your processor which is driving it. So displays as such by themselves they cannot hang. Okay, it's whatever is driving them that can hang. So that's what is the issue. How AMOLED display is less energy than LED? So very simple. So let's say if you have an LED based display, what you have is basically a white light, right? So the backlight is composed of many light emitting basically something which is called a a tandem light emitting diode, which means that you have the red, blue, and green on top of each other. Okay, they are not patterned. Okay, there's no pattern in technology which has gone in there. So the red, blue, and green are on top of each other. You're driving that white. That white is always on, right? So if you're looking at, let's say, a LED TV, all that white light background is always on, right? And then you're using color filters in the front to filter out red, blue, and green. While in an AMOLED, if you want to turn something off, if you have a black portion in let's say, an image, you basically turn off all those OLEDs, right? So of course, which means that you're using much less energy, right? You're not always, you don't have, and then of course, depending on what intensity which you need, you can change those intensities, right? So your back white LEDs glowing at a much higher intensity, while you're actually, it's a wastage of a lot of energy, right? Because all your color filters are filtering things out. But here you're just turning it on and off, depending on what kind of intensities which you need. How the semiconductors molded as chip? I think this is again, we should ask it in a different seminar where we are discussing chips. Different between AMOLED and QLED. Okay, so there's a quantum dot-based light emitting diodes. So here we are using this organic materials, while there you are using quantum dots, right? So basically, if you look at the physics, it's not very different. However, the materials are of course very different, and hence that's the difference, right? So that's basically the difference between AMOLED and QLED. Yeah, I think that's the same question which is in there. For bulk crystal samples, why are the conditions applied to get expected? Okay, so for bulk, what happens is that the electron and holes in a crystal, for example, let's say, even if I take something which is a direct bandgap semiconductor, the electrons and holes have they are so highly delocalized that they don't meet and form an exciton. So if you look at it from excitonic point of view, the exciton has binding energies which is, let's say, a few tenths of millielectron volts. Okay, now you know that room temperature is 25 millielectron volts. So that's enough to break this exciton. So you do not get any light out, and that's the reason you need to have, if you are growing bulk crystals, you need to have some kind of a quantum dot or a quantum well. And that's one of the questions which was asked earlier: quantum dot based OLEDs. So that's which is required. Okay, so same thing again, AMOLED and QLED, which I just answered you. Found any data which could relate efficiency versus cost? Yes, we have lots of data on efficiency versus cost, but we are not talking about the business part of it today. But one thing which is, of course, I mean, exactly, it's not just the efficiency per se. It's, of course, you can make much more efficient devices. And the cost of the device may be the same, but maybe a long-term cost on the, looking at it from the energy point of view, may be different. Okay, so while it may cost the same to make it, the long-term cost may be different, because you'll be driving it at a much lower point in your in your EQE, in your intensity versus EQE curve. Okay, so that's what it is. So how AMOLED have edge over OLED? It does not. So AMOLED has OLEDs in there. Okay, so basically it's OLEDs which are sitting red, blue, and green. You can think of it as islands, right? I showed you that picture, islands of red, blue, and green sitting on this active matrix, and then you're driving it. Okay, so that's what it is. When can we expect this displays with TADF materials? TADF has many, while it does have a lot of advantages of as far as efficiency is concerned, it suffers from one large disadvantage, which is the roll-off. I showed you that graph where you saw that the EQ is rolling off, or the EQ is decreasing with the increasing of intensity, right? So as the intensity increases, the EQ rolls off. So that is one big problem with TADF materials, because of something which is called triplet annihilation. So these excitons come and see another exciton, and then they break up, right? So so a lot of we, as well as a lot of different groups, are working on it. So if that roll-off is reduced, this is a very good question actually. If the roll-off can be reduced, then one can look forward towards TADF. But then again, color purity is much better than phosphorescent. So if that roll-off problem is addressed, I'm sure that TADF will be there very pretty soon. Yeah, my email ID was there in my first slide. Maybe I can share it afterwards again. What are the present scenario of transparent display hurdles? Well, I won't say hurdles as such. So I think it's still concentrated, meaning that the technology has not really changed much, right? I mean, if you look at the technology, it's that mask technology, which is the same from what you had 20 years back. So I think it needs a change in technology, and this is what we plan to do. And hopefully, if that is done, then I think we should see a much more I mean, I think then that will make or enable. I mean, I think that will be an enabler in some sense towards people who would like to get into this business, but can't because of this very large capex cost. What is the problem with AMOLED display? There's lots of okay. So I only showed you the advantages. Well, as far as lifetimes are concerned, lifetimes have now become much better. What I would say is that rather than problems, I would like to look at next generation, which is the blue. I think the blue has to be addressed. Blue is still fluorescent, right? Which means that you're using only an internal quantum efficiency of 25%. So if you can address the blue, I think that will address a lot of things. And then of course the red and I also talked about phosphorescent materials using phosphorescent materials use something like iridium, right, as a core. So just to have this phosphorescent emitters, and that's something which is also not something which you would like to avoid. So maybe the TADF comes in there again, where if you can go away from phosphorescent into TADF, then basically you're going away from this iridium-based emitters, and that's also a very good thing to do. What type of organic molecules you use to make AMOLED display? I didn't talk about too many materials. There's lots of materials. I think you can find it out. I mean, I don't think that's. I mean, you can. I mean, I gave you one example of something which is called ALQ3. It's one of the earlier materials, but there's many materials. I think you should just look at some of the papers which I referred. I showed. And you'll find those materials. How are the newer mini LED display now? So. I'll come to this question. Okay, so the newer mini LED display, so not mini, if you are talking about micro displays, which is this very small displays, this is something which may be used for AR, VR applications. They of course means that, your pixel densities are much higher than what you have in your phones, right? So in your phones, you're looking at, maybe some 2 million pixels over that area, right? So while when you're looking at the, let's say some display where, let's say next generation, like a Google Glass kind of a thing, you would like to have these pictures to be projected into your eye, right? So which means that you have to pack in many more displays, which means that you have to have a new kind of a technology. Your the mask based techniques has serious problems, which means that you cannot make AMOLED displays at this point in time with those masks. So you have to have some kind of a new kind of a mask. Okay, so there are these new kind of masks which are coming in. But then you also need to change your substrate, because you cannot work with the substrate. The substrate which we use are low temperature polysilicon. So those mobilities are also not big or high enough. So this means that you need to change. You need to change substrate technology, which means that the switching technology which goes behind the OLED, as well as of course the way the OLEDs are grown. So I think this requires a lot of work, and there's a lot of interest in there too. And we are also working on this. Okay, yeah, this is also done. Okay, can we control blue light without decreasing the quality? I don't know what is meant by control blue light without decreasing the quality in brightness. The brightness, that's one of the reasons. Of course, blue typically tends to degrade so faster, and that's the reason you typically have the blue pixels larger, which means that you get the same light output, but with lower current densities, right? So that's one reason. So you're driving the blues at lower current density, so the blue pixels are larger. That one has to, most of the time, this so one has to then look at material qualities in order to reduce the the degradation which may happen. Can OLEDs replace laser apart from display applications? Can they be made? Yes, of course, they can be used in medical fields, but an OLED can be a laser, right? So basically what you need to do is that at the end of the day, either you can have a laser which is pumped optically, or you can have a laser which is pumped by electrical means. So if you are driving an OLED to such high intensities that you end up with lasing, right? That you actually have stimulated emission, then that basically becomes a laser, right? So you can see this in the width of the emission becoming very small. So but then what happens is that if you are driving at that high intensities, typically the OLEDs, either their efficiency drops off, or it fails. And I showed you a couple of on one slide I showed you that the exciton polaron interaction, right? So that there I showed you the exciton polaron interaction happening in a field effect transistor. And I believe that if you are going to make an organic laser, it's mostly going, or probably going to be not in a OLED kind of a geometry which I showed in here, but rather in a field effect transistor geometry, because it offers a lot of advantages. What happens is that the light is basically emitted in the channel region, probably far away from the source drain contacts, which means that the light is being emitted from a point where it's very far away from any kind of metal, which means that you reduce a lot of quenching, which may happen because of metals, as well as, in a transistor you can pump in a lot of more carriers, right? The charge density in a channel is much higher compared to what you see in a, let's say, sandwich kind of an OLED structure. So typically this OLED, it's then going to be an OLED, right? Organic light emitting transistor, rather than organic light emitting diode. And I believe that's going to be the structure if it really is successful in laser. So this technology is expensive. It's not very expensive, right? I mean, you're buying a AMOLED display-based phone for 12,000 rupees. I mean, it's not much at all. I mean, that phone has a display, that phone has the electronics, that phone has a battery and whatever casing and all kinds of sensors sometimes, right? So I don't think that's much expensive. But of course, people are trying to get costs down even more. However, I will see how much more the cost can come down. But I won't say that it's very expensive. At this point in time, how graphene it won't enhance. Graphene. The good thing about graphene is that it got the carrier mobilities are very high. So, if you're trying to make contacts with graphene, right, or maybe you're trying to make the transistors out of graphene, then you could maybe make them extremely fast. But then graphene doesn't contain any carriers, right? They're undoped. Okay, so you have to then dope graphene. That's why when I showed one of the work which we have done, where we have doped graphene and we try to understand doping in graphene. So if you can dope graphene, at the end, remember, it's conductivity, right? It's or conductance. It's not just mobility. It's not just the carrier density. It's the product of carrier concentration as well as mobility, right? Sigma, which is your conductivity. Sigma is Ne mu. N is carrier density. Mu is mobility. So you have to have both to be high. And in order to have graphene working efficiently, one needs to dope it efficiently. So that is something which needs to be done. Okay, again, this I answered. AMOLED consume less power compared to LCD is done. Sir, does AMOLED have liquid? No, there's no liquid in there. Okay, and we don't need liquid. We don't want liquid actually in any of this, because liquids are messy, right? Extremely messy. So they're all solid state, right? So that's why these are solid state devices. They're all thin films, right? So these are thin films. What is the difference between OLED and AMOLED? So they are the same. I mean, the OLED is basically sitting on an active matrix substrate. That's what it is. QLED are actually LCD displays which either a quantum dot. Okay, so that's okay. So I think Raj has so the quantum dot with the color filter. I'm a computer science and want to learn electronic circuit and display tech. My question is where and what is a good resource for learn? Is it possible to use AMOLED display and drone technology in future? So, I mean, I don't know why you want to use the AMOLED on the drone, because there's no human being sitting on the drone to look at your AMOLED. But you may use the AMOLED on the ground, right, while the drone is taking pictures. So the AMOLED is basically projecting pictures, right? It's not a sensor. It's not capturing any image. But you can have OLED based. Let's say a camera, for example, if that's what you're saying. In the drone. As far as your electronic circuits, I think maybe that electronic circuits and display tech. There's no such display display course given in any universities, but we plan to start a display-based course that should happen soon, at least in IIT Madras. Yeah. So again, Raj has answered for the mini OLEDs. Why blue light consumes many? Blue has lower efficiency. It's fluorescent-based material, so its internal quantum efficiency is limited to 25%, and that's why you need to. So EQE is lower. Yeah. So again, Raj has answered for AR VR application for the micro OLEDs. Let's see, instead of mask, any possibility to use photosynthesis or digital litho? We don't want to use any litho because, these organic materials, if you are using photolithography, for example, you'll basically wash away this material, so that's not good. Photosynthesis, I think, is a very different process. Yeah, we're not we are not making plants in here or any kind of method by which to generate energy, but one can think of having little solar cells on top of, or, AMOLED displays. So let's say transparent cells where you can harness maybe the NIR region, right? NIR is something which you're not seeing, right? So NIR and NIR, there's a long tail of NIR from the sun, so that's possible, at least to make a small solar cell. Okay, thank you, Dr. Shoma, for very nice introduction from the 6th level of engineering. Okay, then regarding the and then can tunnel FETs be used for okay, so can tunnel FETs be used in LED configuration? So at this point in time, if you look at the material which is used for a field effect transistors, it goes in the background, right? So this is not in the LED. Okay, so there's no field effect transistor in the LED. The LED is a sandwich structure, right? So the transistor is at the back, driving the LED, so driving it to a certain level, current densities, which means to a certain light intensity. And if you want to use a tunnel FET, you basically what will happen is that, yes, if you want to, but then you have to look from the cost point of view. And at this point in time, what you're using as a very simple field effect transistors using low temperature polysilicon. Okay, so if you're using tunnel FETs, then you're going towards very high, well-defined crystalline material as your field effect transistor. If you are going to a 355 kind of a material system, it's going to be very difficult because it's going to be highly costly. So it has got to do with something which is of low cost, and then of course crystalline in nature. Then right now what you're using is polycrystalline. OLED light affect any plant growth? I don't think so. I don't think the LEDs are watching any AMOLED display unless you have a plant behind you, but those intensities are pretty low. It's the sun intensities are much higher, right? So 100 milliwatts per centimeter square is your sun. OLEDs are nowhere near that. So I would rather it's better you keep them outside rather than shine have a white OLED shining over them. But if you wish, if you can reproduce the solar spectrum with the same intensity, why not? At the end of the day, they are just photons falling on the plant, right? They don't know whether it's coming from the sun or from somewhere else, as long as the spectrum remains the same, right? So yeah, go ahead. Why don't off backlight produce black color in LCD? We can't turn off the backlight, right? The backlight is always on. Okay, so you're changing pictures. You just can't turn on and turn off the backlight. Your pictures are changing very fast, so your backlight is not going to turn on and off that fast. So that's not the solution. Okay, I don't have any more questions, Richu.
Okay, we can close then.
I think so.
Yeah.
Yeah. So I think that's it. Then thank you very much. Thanks for joining, and also Richu, thanks for introducing us.
Anytime.
I hope this was helpful to the audience. Yeah. Thank you very much.
Thanks a lot. Thank you so much, Professor. It was our pleasure to host you, and I'm sure all of the participants had a wonderful time listening to you, and you've taken so much time to answer all of their questions also. So thank you so much, sir, and thank you to everybody on the panel. Thanks a lot, and thank you to the participants as well. Have a good night. Thank you.